3.4, where we're looking at rational functions of the form ax plus b over cx plus d. So we've looked at reciprocals of linear functions and reciprocals of polynomial functions. Today we're going to be looking at functions that are a polynomial over another polynomial. We'll start simple. We'll start with linear functions over linear functions. So first we need to take some time to look at key features of a polynomial, and we'll start by looking at key features of one of these functions, and we'll start with an easy function. We'll look at the function x divided by the function x minus 2. So we'll start by looking at the x-intercepts. X-intercepts happen when the y value, or the function, is equal to 0. And in the past, when we've done this, our first step after we've set the function equal to 0 would be to cross multiply. And when we cross multiply, we're going to end up with 0 equals x. In the past, we had a number where the variable should be. We had something like 0 equals 1, which was false. But now that we've replaced that with a variable, this is now a true statement. X can equal 0. So therefore we can say that the x-intercept is at the point 0 and 0. It's at the origin. We can do the same thing for the y-intercept. Y-intercepts happen when we evaluate the function at 0. So f evaluated at 0 is going to be 0 over 0 minus 2, which we can simplify to 0 over negative 2. And this is also a statement that we can evaluate. Okay, 0 divided by a number is just equal to 0. Okay, it's when we have a division by 0, a number over 0, that we have a statement that's not true. So in agreement with our x-intercept, we're seeing that our y-intercept is also at 0 and 0. Okay, continuing on, our vertical asymptotes, those are asymptotes that go straight up and down, and they happen when our denominator equals 0. So we need to find out which value makes our denominator equal 0. And that would be x equals 2. So we have a vertical asymptote at x equals 2. The last thing we want to look at are our horizontal asymptotes. Those are the asymptotes that are flat, move across like the x-axis. More specifically, horizontal asymptotes happen as x gets closer and closer and closer to positive or negative infinity. So we can evaluate f of x at a very large number. And here's a problem. I have a very large number, and if I take the number, or the concept infinity, and I subtract 2, I still have infinity. So I have infinity divided by infinity. This isn't as easy as saying this is equal to 1, because, and we can talk about this in class, one of the properties of infinity is that one infinity could be larger than another infinity, and we don't know which one's which. So we don't know how to evaluate this statement, infinity divided by infinity. So let's look at this a different way. Let's divide each term f of x by x. So my function is now going to equal x over x all over x over x minus 2 over x. Simplifying, x over x is just 1. So now I'll have 1 over 1 minus 2 over x. And here again, we can imagine pushing our variable towards infinity. I have 1 over 1 minus 2 over infinity. Any number divided by a larger number approaches 0. So that term of 2 over infinity is going to become 0. So I end up with 1 over 1 minus 0, or just 1. So I have a horizontal asymptote at x equals 1. Now we can take all this information and we can graph it. I'll start by filling in my scale. Once I've filled in my scale, I can mark in my key points. So I have a vertical asymptote at x equals 2. I have a horizontal asymptote at, pardon me, I just noticed a mistake. This should say y equals 1. Our horizontal asymptotes are equations with respect to y. So that horizontal asymptote should be at y equals 1. Apologize for that. The other key point I need to mark is my x and y intercept, which just happen to be at the same point this time. And then I need to check my behavior, if I want to be really sure of how this graph looks, around my asymptotes. So the last thing you need to do before you graph is check behavior around the asymptotes. What I mean by that is find out what happens as x approaches 2 from the right, as x approaches 2 from the left, and as f of x approaches plus or minus infinity. Okay, you should try those things on your own. So once you've tried this on your own, you should see that our function approaches the horizontal asymptote of 1 as x gets closer to negative infinity. And then as we move towards the vertical asymptote at 2, our function approaches negative infinity. And on the other side of the asymptote, our function is going to approach positive infinity as we approach 2 from the right, and then flatten out and approach the asymptote at y equals 1 as our function, our x value of our function, gets towards positive infinity. So our graph is going to look something like this. So what you can do for homework right now is graph these three functions, f of x, g of x, and h of x. And in class tomorrow, we're going to look at how the coefficients of our function affect the behaviors, how A, B, C, and D affect the behavior of our functions. So try and graph these three things. I do want to tell you one shortcut first, and that's a shortcut to find horizontal asymptotes. So when we did my first example, to find the horizontal asymptotes, we divided all terms by x. This takes a little while, so there's a shortcut. When we have any rational function that has a polynomial over a polynomial with degrees n and degrees m, if the degree on top is less than the degree on the bottom, then the x-axis is the horizontal asymptote. So we've already seen this when we had a function like 1 over x minus 2. This is the reciprocal of linear functions, and our horizontal asymptote was always the x-axis. If n equals m, if the degree on top is the same as the degree on the bottom, then the horizontal asymptote is the line that's represented by the coefficients of the highest degree term, a over b. So these would be functions like what we just looked at, 2x over x minus 5. My a value is 2, my b value is 1, so this would have a horizontal asymptote at y equals 2. And then the third case, and we're going to look at this later, is when the degree on the top is higher than the degree on the bottom. There's no horizontal asymptote, but as we're going to see in the next week, we might get a slant or a diagonal asymptote. Okay, and this would be something like f of x equals x squared over x minus 2. There's no horizontal asymptote, but there might be a slant, a diagonal, or an oblique asymptote. So use this shortcut to help you graph these three functions, and then in class we're going to explain the coefficients, the effect these coefficients have on the function, and we're going to look at finding some shortcuts. Thanks for watching.